Welcome to ETAP webinar, Stability Studies for Power System with DERs. My name is Mohammed Zadeh and I'm your presenter today. In this webinar, first I introduce ETAP Transient Stability module for those who are not familiar with it. Next, various ETAP models, specifically VEC models for distributed energy resources, will be reviewed. Then we will demonstrate how these models can be used for system planning studies. Later, we will discuss DERs, distributed energy resources, interconnection studies, reviewing why VEC models fall short and the importance of using vendor-specific or black box model for such studies. We'll discuss about challenges of such approach and how ETAP can support black box models provided by vendors. We will also demonstrate a generic model provided by ETAP for inverter-based resources that can be used in the earliest stage of design where vendors have not been picked yet. As part of ETAP 20, a new feature recently released that allows to simulate inrush current within transient stability analysis with good accuracy. This approach is good enough for many designs and protection settings application. We will have a quick demo of this feature and how it can be used to evaluate the effectiveness of pre-magnetizing transformer to reduce inrush current. In this webinar, we also use the new plot view that is a new feature in ETAP 20 throughout all the demonstrations. Finally, I will summarize this webinar. Transient stability analysis enables engineers to accurately simulate power system dynamics and transients via system disturbances and other events. ETAP Transient Stability leverages detailed and validated equipment and protection characteristics, control models, and user-friendly graphical user-defined modeling together with advanced algorithms to perform analysis for industrial to transmission power systems. A link to the Transient Stability module is provided here as you see, and I would like actually to switch to the web page and go through the details of this module. This module has tons of capabilities. You can calculate critical fault clearing time, you can do short and long-term transient simulations, you can confirm your generator rotor angle stability, you can do dynamic acceleration and reaccelerations of your motors and the power system. You can do identification and testing load shedding techniques and relays. You can compute and test fast load sheddings via fast bus transfers and many more things that you can do within this module. This is a very well developed module over many years, and again, for all the details of what we have been providing in this module over the many years, you can go to the website of the ETAP and look at the transient stability product and look at all the details and all the capabilities and features available in this software. For those that are not familiar with this module, I'm going to go ahead and quickly demonstrate few capabilities of this module so we become familiar with this module. So later on we can go ahead and focus on the distributed energy resources model. The base foundations of any transient stability module is the models or dynamic models for the rotatory machines, generators, motors, power system in general, and also when it comes to the distributed energy resources like wind, solar, battery is the models for those assets. So in ETAP, as you see that we have a very detailed model for the generators, and then we look at also the mechanical aspects of the generators, looking at the inertia, damping factors, the torsion effects. User can have built-in or user-defined exciters, governors, power system stabilizers. The same thing when it comes to the motors, you can have again your motor models, and then you look at your basically different details, the dynamic models of the motors. You look at your basically again inertia. You can have exciter for your, let's say if it's a synchronous motor, you can have the load model. Again, ETAP has been providing the detailed modeling, dynamic modeling for rotatory machines for a long time, and these models have been well proven. So what I would like to do here, I want to do a very quick analysis as a demonstrations. So what we are trying to do here, we are going to put the fault at this bus 6 here, which is kind of close to the generator here, the generator 1. And basically we do that through the, again, transient stability module. We go through the events. We have defined a 3-phase fault at bus 6. And then we are removing the fault after 180 milliseconds. Again, in transient stability module, you can have lots of actions and events that you can introduce for different type of the asset. You can have different fault types, line to ground, line to line, and then you can open circuit breakers, close them, and then many other events that you can do here. Let's run this analysis for around 10 seconds. You can look at actually the sequence of events that what happens. As you see here, we had a fault close to the bus here at the generator bus. It was bus 6. The voltage dropped to 2.61% here. As you see on the screen, you can see that fault got clear, voltage comes back, and the generator starts acting. Now, for seeing more details about this, you can go always to the generator and you can plot various quantities for this generator. We can look at the basically the relative and absolute angle of this generator. As you see that the angle goes about, let's say, 157, it comes back and it becomes stable later on. Once we clear the fault, you can look at the mechanical power, you can look at the electrical power that goes almost to 0 during the fault. You can look at the excitation, you can look at the governor, active reactive power, speed of the generator. It accelerates due to the fault, and once the fault clears, it decelerates. You can look at the scene reactance from the generator perspective. You can look at the locus of that and see how basically the generator behaves. So in this case, actually system is stable and you can look at everything. Now if I go to the case that actually generator is the same case, but I've increased the fault to 190 milliseconds. So basically we keep the fault a little bit longer. So if I run this as bus 6 fault unstable, so I've done it before, so I know that it gets unstable for this scenario. So I'm running it one more time. So basically when you run this, you can go ahead and actually plot the generator quantities. And as you see here, even though it is stable, but look at the absolute angle, we already slipped the pole, we passed the 180 degree. So once you pass the 180 degree means that this system is not gonna survive, and typically there is an out of step protection that trips this generator when typically the angle gets close to 180 and even sometimes less than that. So in this scenario, in a real system, your generator trips, but when you're looking at the angular stability perspective, in this scenario was around 180 milliseconds. So that's one application that can be used for the transient stability. The second case that I would like to show here is the loss of excitation. So in this scenario, what I'm trying to do is I'm putting an event for the generator 1, and we have an event for loss of excitation here. You see that there are tons of other events here that you can do. You can increase the generation or reduce the generation. You can do voltage impact or ramp through the excitation systems. You can switch from the isox to droop mode. You can start the generator, stop the generator. So in this case, you have a loss of excitations, and as just representations of the loss of excitation protection system, we actually trip the circuit breaker 4 at time 3 seconds, after 2 seconds of loss of excitation. I want to see how the system behaves during the loss of excitation and then after that loss of the generator. So if you look at this case, we run this case for again around 10 seconds, and we can now go ahead and look at the generator, let's say performance. In this case, again, we are going to look at here that during that time that we lost excitation, the generator angle actually increased, and you see that generator starts here absorbing lots of reactive power. Basically your machine, which is a synchronous machine, gets converted into the asynchronous machine. Reactance actually from here goes all the way down to here up to 3 seconds, that when we trip then the reactance actually becomes 0 or infinity. In that sense, that is not anymore valid. So basically you can see the trajectory of the reactance that is important for several protection settings. You can see how the system behaves. You can go actually look at the system different places. You can look at the bus voltages. You can pick a bunch of bus voltages here, and you can actually plot the voltage and see that how the voltage across the system is. As you lose, generator loses the excitation, you see that voltage across the system starts dropping, and you can see now what happens with that. So again, this is another example that how transient stability analysis can be used to look at the dynamic performance of the system. Another application that is very interesting that I would like to demonstrate here is the bus transfer, especially in the industrial applications where you have a load that is supplied, can be supplied by the two sources, and once we lose one source, we want to go ahead and switch to another source. But when we do that switching, we have to be careful. So in this scenario, basically I have two sources and a normally open switch. I have a large induction machine here, and what we are going to do, we're going to trip this circuit breaker here. If I bring the event list here, okay, so we're going to trip this circuit breaker, and at 0.5 seconds and 20 milliseconds later, we are going to close the tie switch to basically move over the motor from the sub 2.2 to sub 2.3. But keep in mind that as we open this switch for 20 milliseconds, this motor is isolated from the system, but due to its inertia, it starts decelerating. So the frequency drops, the speed drops, the voltage starts dropping. But if we are fast enough to close this circuit breaker, we can actually energize back or connect the induction machine to the other source while not jeopardizing the safety of the system. So for successful fast bus transfer, typically what we do is that we can put some criteria here, is that, okay, you do the fast bus transfer only if the angle is less than, let's say, 30 degrees between these two buses, and if the voltage angle difference, let's say, is less than 30%. We can put also the frequency deviation limit as well. So for this case, actually, if I run, so what will happen is that ETAP simulates the system, simulates the induction motor that is actually isolated from the system. And what will happen is that this scenario is the case of a successful, basically, isolation. So as you see here, we isolate the generator, the induction machine, but is still decelerating. If you look at the speed, it's decelerating, and during that time that actually it was isolated. So it was decelerating as the time goes by. I'm going to plot this for you for the sake of better clarity. But because the angle's magnitude at the point of connections is less than 30%, the angles are close together, it allowed the transfer happen. So as you see here, we got the closure successfully. Okay, let's plot the results for this fast bus transfer. Let's plot the results for sub 2.2 and sub 2.3, the two buses that we are transferring between them, and we are look at the voltage, frequency, and angle. Let's start just by looking at the voltage and voltage angle. As you see here, I have around, if I put the crosshair, I have around, at the time of closure, I have around -1 degree on one side and -23 in another side. So I have around 22 degree, which is less than 30 degree. And then I have around 100% at one side and 80% on the other side. So it's both of them less than 30%. So in reality, transfer happens successfully. Now let's do the unsuccessful fast bus transfer. So what we are doing here is that we have the same scenario. We are closing after 20 basically milliseconds, but the only thing here is that we said that our angle should be less than 20 degrees. So last time was actually 21 degree. So if you run this case, bus transfer fail. So if you run this case, what's going to happen is that because the angle at the time of closure was above 20 degree, what's going to happen is that the ETAP says that the sync check failed, and it didn't move forward. So the motor actually started decelerating. So in this scenario, if we go and actually plot motor 9 and we plot, let's say, just the slip and V bus, V terminal, and we try the megawatt electrical, mechanical, and we plot this, you can see that the motor is actually stopping, and the voltage goes down, the power goes down, the sleep goes up. Basically, the motor is going to stall. Again, this was another good example of the application of the transient stability module. So with that, I'm done with my introduction to the transient stability module, and I would like to now go back and focus on distributed energy resources model. ETAP offers dedicated elements for modeling distributed energy resources, including wind, PV, battery, inverter. When it comes to transient stability and dynamic modeling of these assets, wind turbine generations type 3 and 4 offer several options. ETAP offered built-in WEC and generic model, which is only for type 3 many years ago. And WEC, for those who are not familiar, stands for Western Electricity Coordinating Council. These are considered our legacy models, and newer models are all based on UDM, which is user-defined models. Within UDM, WTG models type 4A, type 4B are available as per IEC 61400-27-1 published in 2015. These are more European models. Also, we offered an ETAP 20 WEC second generation type 4A model that is based on latest WEC models. So later on, I'll go through each one and actually show how they look like and where you can find them. Each wind or solar plant, when we are talking about plant, I'm talking about farms with many winds, turbines, and many PV arrays. They are equipped with a power plant controller to control, coordinate, and manage the entire plant. As part of a stability studies, it's important to consider the impact of power plant controller on transient stability analysis. For those who are interested, ETAP had a dedicated webinar on power plant controller that you can watch. Okay, now let's take a quick look at where you can actually find these models. So if you go to your, basically in edit, we have a wind element, a wind turbine element, which we're calling it WTG. As you see that this WTG can be used for basically different type of studies. We covered a short circuit, we have load flow, time domain load flow, reliability, harmonics. And when it comes to the transient stability analysis for type 3 and 4, so if you go to type 3, we support three type of the models: WEC model, which is a legacy model, and then the generic model, and then the UDM. So let's go through each one quickly. For the legacy model, basically you can go to the control page and you can see basically the details of the model. You can go to our help and see how basically this model works, what are the parameters, and then the reference to the material, to the place that this model is taken. For the generic model, again, is a legacy model, is a very simplistic model. Mostly what we recommend right now is actually the UDM model. So in the UDM model, that when you go to the WTG and click basically on the UDM, and let me select nothing here and go to the UDM. As you see here, we also provide 5 user-defined model for the UDM. And we have, as I said, the type 4A, type 4B, which are more European type models. And you can look at them, and there are tons of documents on the web that you can find to look at what they do. So basically, as you see here, even the details of the model is available for you. And again, it has different modes of operations, and we capture various aspects of it. And this is as per the IEC standard. All the parameters of this model are in the model parameters that you can put here, and then you can compile and use it. There are, again, type 4B, and then type 4. There's also type 4B, as well as there is VEC model. So let's take a look at the VEC model. This is the one that I'm going to today use for the demonstration purpose as well. In the VEC model, as you see here, we have captured all the blocks that's needed, control blocks that's needed for this model. There is a basically guide that helps you how to set this model as per the VEC document. But in order to use this, you need to be familiar with the VEC model, go through the documents and the references provided in the UDM and look at them. But in reality, what it does, it models the WTG as per this document, and we have validated and tested this model. Now, again, once you selected this model as a UDM, now this WTG is going to behave like a VEC model. We also have the power plant controller, and you can go and get the REPCA here. And once you compile this in your project, it's going to work automatically for your wind, to command the wind to go up and down. Again, is a coordinator for multiple wind generation in your system. So this is again as per the VEC document. Again, the references are provided that you can go and take a look. When it comes to the inverter-based resources, or which are most of the DERs are like that, the philosophy behind the modeling is using a concept called current source injection. So in reality, the behavior, the dynamic behavior of the DER is mostly dependent on the control system. And the way that this modeling is done in transient stability softwares is that the control system defines basically the direct and the quadrature component of the current that needs to be injected to the system based on typically the voltage and power measures at the terminal of the DER. So in this case, in a transient stability, what we do is basically the UDM, which is the ETAP user defined model. The control blocks there measures the voltage, measures the power and currents, and then based on that determines how much current needs to be injected to the system. And this philosophy of control and modeling is identical for WTG, PV, and BS, though the control block diagrams could be slightly different. So we use the same element, which is the WTG for now, and you can pick a different UDM for your battery. If you want to model a battery as per VEC 2015 document, you can use the same WTG element for a dynamic performance and just connect the UDM for battery or connect the UDM for the PV. So let me just do a quick demo to show where you can find these in ETAP. So in ETAP, if you pick a wind element for now, and you go to the UDM, basically you can actually go to the gen load folder within the ETAP, in the UDM, in your ETAP, in the UDM, go to your gen load, and here you can actually have a battery model that you can pick. We have older energy storage models, and we have also a PV model. So you can pick one of these models. So let me pick one of these for you. So I've already picked the PV model. If you open this model, you'll see that basically this is a generic model for distributed and small PV plants. And this is as per VEC model. All the references, documents where the model is in the UDM. And you see that basically all the control blocks, how things are connected together. And at the end of the day, as I said, we are injecting just currents, the direct and quadrature component of the current to the basically to the system. I also have a similar case for the battery. Again, you can use the same element and you can pick a battery UDM in ETAP, and you can actually model the battery. We have a dynamic behavior or model based on the VEC in the basically UDM. So you can take a look at it here and see how things are connected, how you can actually utilize this model to emulate the dynamic performance of your battery in the system. Also, we have our lump load in ETAP 20 can also have a basically UDM, and can be used that for regular lump flow dynamic models for the lumps, but as well as it can be used again as a current injection source to simulate or model the dynamic performance of the different DERs, batteries, and stuff like that. In the next major release, we're going to support dedicated UDM for inverters, PV inverters, battery UDM. As you saw that you can still use ETAP 20 to do that, but you need to use either WTG or lump loads, but elements. But for in the next release, you can use inverter, PV inverters, and battery UDM independently. You don't need to use a separate element or a different element for that purpose. Okay, there are typically two types of the studies done, at least for when we are integrating distributed energy resources in the system. So one study is basically you want to make sure as a system operator, system designer, that integration of the renewables will not have a unacceptable performance during the system disturbances. So you want to investigate to make sure that the impact of the DERs on your system dynamic performance is acceptable. So that's called system planning study. Typically, you're looking at the dynamic performance during the frequency changes or small voltage drops or sudden changes in the system variables. Or if you have a bunch of wind farms or solar farms close together with a battery, you want to make sure that their controllers are working together in a coordinated manner. You want to, if you're commanding as a power plant controller or as a system operator to change some set points, or you want to make sure that that change is smooth and it's not impacting your system in an unwanted manner. So again, the voltage and frequency support, those are all system planning studies. So let's have a quick demo of what is system planning study and how you utilize these models that we discussed, the IC models, the WEC models, or the models that you can do yourself through the UDM, and see how you can utilize and use those models in ETAP to do system planning studies. Okay, one of the key studies that needs to be done is the voltage control of the wind plants or systems. And in this scenario, what I would like to show, I have just a standalone wind here, 2.5 megawatt. And what I would like to do, I would like to see that how it can maintain its voltage after we basically change some voltage on the utility side. So what we have in ETAP, actually, you can actually create an event for the utility. And what we do, we are ramping up the voltage 1% during 1 second. And then after about 10 seconds, 9.5 seconds, we are ramping it down by, again, 1% during 1 second. And we are running the simulation for 25 seconds. And we would like to see how this wind farm or wind turbine, we want to see how this wind turbine actually responds. So when I run this simulation for 25 seconds worth of simulation, we would like to look at the terminal voltage of the WTG. We would like to look at the active reactive power and the, basically the performance of this wind turbine. So let me go ahead and look at the bus. We are looking at WTG bus. We want to plot the voltage first. And then what we would like to do, we would like to go again to same WTG and look at the voltage of the terminal megawatt and megavar. So I have all quantities. And I would like, actually we can see all three here together. So as you see here, this is a terminal voltage. So at 0.5 seconds, you have a ramp that brings up the voltage. As the voltage at the utility side goes up, voltage at the terminals of the WTG goes up. So immediately the wind turbine is going to start responding. So what it does, because voltage has gone up, it tries to absorb more and more reactive power to bring down the voltage to 100%. And then here what it does is, as you see that as a consequence of that, a little bit of the active power drops too. And then at 10 seconds, what we are doing, we are actually ramping down the voltage. So voltage starts dropping. And once the voltage drops less than the set point, which is around 100%, once the voltage drops, basically the wind turbine starts reducing the absorbed power, and this results into bringing up the voltage to close to 100%. So if I let the simulation go for longer time, you see that actually the voltage will come back to the 100% if we have enough reactive power capacity. So this is one case that is important to do to see that how the wind turbine actually performs. Again, you can go ahead and switch to the fixed power. So let's say if this wind plant has if I go to the UDM and say that no, rather than have a voltage control, I want to have a fixed reactive power control. Okay, so if I go to this wind turbine here and say that in the V flag according to the VEC, I can put this 1 and this put 0. This make it actually Q control according to the VEC document. So if I compile and close this, so what happens here is that if I run this case, okay, so let me just run this case one more time. Now it is in the reactive power control. So my expectation is that after all these voltage up, voltage down, what the inverter of the WTG is trying to do is trying to maintain the reactive power of the WTG. So if I plot just the, let's say the voltage turbine megawatt quantity of the WTG here, you see that the wind plant is trying to maintain the reactive power regardless of the voltage changes. There is some transients always, but the control system is doing a good job to bring down and make sure that the reactive power is well controlled. And typically in a power plant, big power plants, each individual wind turbine is in the Q control, and there's a power plant control itself that commands the Q to adjust the voltage at the point of interconnection. So you see that this is now a different performance depending on different settings on the WTG. Okay, the next set of studies that typically need to be done by the transient stability analysis is interconnection studies, and typically is to looking at the far right through capability of the DER, and that can be as well low voltage right through, high voltage right through. We can look at the low and high voltage protection and low and high voltage frequency protection, frequency right through. So those are the studies that basically needs to be done for interconnection study for any integrations of the considerable amount of distributed energy resources. Now, when we are talking about the voltage right through, whether it's a fault or low or high voltage right through, just to understand what it means that during the fault, when the voltage at the terminal of the DER drops, the DER is not supposed to immediately trip. So basically, like generator in the system, it needs to stay there for a certain amount of time and be able to feed reactive power to the system to improve the voltage profile of the system or support the system during the fault. That's why sometimes it's called a voltage support or right through. So different grid codes define basically different ways of to do the right through, but there are two key components here that needs to be understood. That first is how long the distributed energy resources needs to be stay and right through the fault or a voltage drop or voltage high voltage, and the second is basically how much it needs to contribute during the fault or the voltage drop or voltage increase. So this is examples from the German grid code, the latest German grid code. As you see here, for instance, what it says is that basically says that at a certain voltage levels, basically let's look at here, let's say at above 25% voltage, let's say the DRs needs to stay at least for 150 milliseconds. Okay, let's say if the voltage is 70%, the inverter should stay at least for 300 milliseconds. So that's how it defines how long it should stay in the system. So that's one aspect that is important. The other aspect is that if the voltage drops, how much reactive current or current needs to be injected to the system. For instance, in the German code, especially in the latest one, it defines how much both positive and negative sequence need to be injected to the system if you have a severe voltage drop during the fault. So it says that, let's say if your voltage drop is about let's say 10%, they have two K factor, K1 and K2, that determines how much actually needs to be injected. For basically many grid codes are still falling behind of negative sequence current injection. Most of the inverters today, they inject positive sequence and they are enhancing to inject negative sequence. So in ETAP also, when it comes to the short circuit analysis, the positive sequence injection is supported, and soon will support also negative sequence injection in the next major release. Now, when it comes to the dynamic analysis, okay, even though grid code defines in some extent how much needs to be injected, how long it needs to stay, but still some of the details of how things are done, how it's implemented is not 100% at this moment clear in the standards, and different vendors may do it differently. And there are certain details here, as you see that there's a negative sequence part here, that typical transient stability is based on positive sequence, cannot support that. And then even here, the voltage drops is not just based on positive sequence voltages. It can be a combination of basically different phase-to-phase voltages. So when it comes to the far right through capabilities, VEC documents or even the IEC documents, they are claiming that these models are not recommended for evaluations of far right through. So the VEC models are designed or developed for system planning studies, where you're trying to study your system and your basically wind farm or solar farm or generation plants are far from typically a disturbance, and you're not looking at events or severe disturbances that's happening close to them, and you're trying to kind of use a generic model when you're studying your systems, and you're not very impacted by one individual, let's say WTG in the system. So you're looking at overall performance of the system, you're looking at the stability of a big transmission system, and you're looking at that. When it comes to the interconnection studies, where you're looking at a very specific basically wind technology and vendor, and you want to verify that it's following the grid codes, it's very important actually to use the vendor model and basically what the vendor does to verify that basically the vendor is doing it correctly. If you use a generic model, you're just verifying a generic model performance, even though they haven't developed too much around the FRT capability. And again, when it comes to interconnection study, part of it, which if I go back here, when it comes to the far right through, low voltage, high voltage right through, or even a little bit of frequency right through, is all you need to use vendor specific. When it comes to protection, you can actually model the protection independently. If those protections are again outside the inverter control, it's just a dedicated relays there, you can actually model them in the ETAP and evaluate their performance. So as I said, there are when it comes to this far right through capability, the modeling is more sophisticated to capture all the protection, all the aspects of, let's say in case of WTG, you have a crowbars can come into the pictures. And then transient stabilities, typically their positive sequence modeling may not capture all the aspects of the unbalanced faults, and again the type of the fault and the magnitude of the remaining voltage at the inverter terminal is important. Typically, VEC models is a model for equivalent of the entire wind farm, while when you go to the far right through, if you model your entire wind farm and fault is at, let's say, at close to the terminal of the wind farm, the voltage at the terminal of the inverters would be very different because of all the cables and stuff that you have in between. So again, a single machine equivalent model does not capture the fault event, okay? Now, what is the solution? The solution is to use a black box model. Okay, so the black box model basically means that the vendor provides the black box model with input output settings, and the simulation software tools communicate with that black box model. Let's say feed the voltage, power, or currents, and then gets the amount of current injected into the system. And unfortunately, there is no standard yet on the black box modeling, and the Greek codes are standards are trying to mandate the vendors of the DERs to provide a EMT dynamic and a steady state models. And but typically the EMT model is available first, because typically they vendors, they wrap the code that they use inside the controller, very similar things or identical things as a black box model, and then provide it to the clients. Now, ETAP offers a user API as part of ETAP 20 to incorporate DLL-based dynamic models. So basically, we provide a C++ interface for inverters and WTGs, where you can have access to the voltage and powers, and you can inject currents back or power backs to the system. And if the vendor has basically already a black box model, they can easily wrap within this black box model ETAP API to create a model that can work with ETAP. And we are working with the vendors to do more and more of these models. The other thing that is important to say is that the EMT model, as we'll see, may be usable for dynamic analysis as well. So what we have done so far, we have taken some black box model, and what we have done, we have wrapped it again using the same API, and we managed to run it during the transient stability analysis. And this is the results of one of the systems that we run in PSCAD and ETAP. And this is for the case of a three-phase fault at the point of interconnection. And as you see, is that the response of the PSCAD and ETAP for vendor-specific model is almost identical. Definitely, there are certain transients in the systems that you can only see in the EMT analysis, and you see it here. But again, when you're looking at the ultimate things, that basically how the system in general behaves, the trends of the voltages, currents, and powers, you see that there's very much matching a lot. The other approach that can be used is basically use a co-simulations. Our transient stability analysis is capable to work with PSCAD. So if you have a vendor-specific model in the PSCAD, you can actually connect it to ETAP and run a co-simulation between ETAP Transient Stability module and PSCAD. And for those who are interested, I think we have a webinar actually some time ago, and you can go to the ETAP and search for the co-simulation, Google it, and you'll find that this webinar, and you can watch it, how you can use ETAP Transient Stability module to do co-simulation. So when it comes to interconnection studies, as I said, there are two approaches that can be adopted. One is to use a black box model. The other one is to use a co-simulation. In case of interconnection study, the other aspect is to do voltage and frequency protection during the transient stability analysis. So ETAP 20 or even earlier versions, we are supporting over and under voltage relays, over and under frequency relays, and then we also do reverse power and instantaneous overcurrents. And in the next major release, actually, we support all protective devices powered by our advanced protection module called StarZ. So let's have a quick demonstrations of the how these protections that is part of the interconnection studies can be modeled in ETAP, and how we can use this actually to do this study. Okay, in ETAP you can use a voltage relay, and the voltage relay provides you the under voltage and over voltage protection. You can define the settings at which the 59 or over voltage will trip, and which circuit breaker to trip and close, and what is the time delay. So I have here 110% settings for over voltage and 90% for under voltage, and I have 200 milliseconds for over voltage and 300 milliseconds delay for under voltage. And basically Again, the very key important thing here in ETAP is that you can have an event for utility. So I can actually increase the voltage. I have a basically sudden voltage increase 15%. I want to see how my actually system performs or my protection performs during this situation. So I'm running the analysis for 15 seconds. So my expectation is that if the voltage of this bus goes above a certain level, so let's see what is that level right now. So we are looking at the percent value, and the voltage impact happens at 0.5 seconds. So at 0.5 seconds, as you see, the voltage at the terminal of the WTG goes to around 113.3%, so it exceeds that 110% limit. And then what happens is that the voltage relay is going to trip 200 seconds after that. And keep in mind that we have a circuit breaker here, and circuit breaker has a trip time as well. So that's considered in the simulation. So when we open this circuit breaker, you see we de-energize the WTG. So that's one case. Now if I go and say that instead of having a 15% voltage increase, I'm going to have 15% voltage drop here now. And if I run this simulation one more time, so my expectation is that the under voltage actually kicks in and actually trips the WTG. So in this case also we can actually go ahead and evaluate the performance of the protection system. Again, you have 300 milliseconds delay and 84 milliseconds due to the circuit breaker tripping time. So you can see that how basically at when and what time the WTG gets disconnected. Again, voltage drops to 84% in this case. ETAP also offers a frequency relay where you can actually set the settings for over frequency and under frequency. As you see here, I put 4% increase for basically over frequency and 4% down for the under frequency with the time delay of 5 seconds. So what's going to happen is that if the frequency goes above 104, we're gonna trip basically the CV here. So my event here actually, again for utility, I've put 7% frequency drop. I'm ramping down the frequency by 7% within 2 seconds. Okay, so if I run this case and go and plot the frequency at a bus, so if you look at the frequency at a bus, we're looking at the WTG bus, we are looking at the frequency. As you see, that frequency from 100% goes all the way 7% down to 93%. So if you look at here, what happens is that the WTG actually trips, and it trips at 6.73. At certain point, the frequency drops below the threshold that we had. I think we set it to 94%. So 94% is somewhere here, and then we are going we set it to 96%. We set it to 96%, and then we are going 4 seconds after that. So if this is 96 here, 1.56, we go 5 seconds delay, should trip at 6.56. So if I go to this here, plus the circuit breaker times that we add, so it becomes 6.7. So the ETAP simulates the protection systems, the tripping, and what happens in the system. Again, the event for the utility really helps to perform the interconnection studies. As part of interconnection studies, it's also important to know that at the earliest stage of each project, even the vendor is not already picked for your, let's say, your inverters or your battery or energy storage or DER. So in that stage, sometimes it's needed to perform some studies, and at the same time, the Greek codes are mandating all the DERs to behave in a certain way in terms of how much they basically inject active and reactive power during the fault and voltage drops or increase, and at the same time how long they stay in the system. So eventually all the DERs based on the grid codes will come to the certain points that they will have more or less similar performance. But so by that time, there would be beneficial to have a proper generic model that can do the low voltage right through, and as well as the grid forming and following as well for certain, let's say, microgrid application when we want to be able to actually go islanded and come back. So most of these VIC models that we discuss, or IC models, they don't support actually the grid forming as well as the low LVRT as per latest grid code. So ETAP offers a generic controller that can be used to implement a basic inverter functionalities for grid following, grid forming, do low voltage right through as per the latest standards. Again, it has the lots of details about you can put in the basically your grid codes informations, and then lots of information about the modes of operations of the inverters. What I would like to show you here, I don't want to go to the details, that what I'm trying to do here to show one case of using transient stability module to do such kind of a study using the generic model that we have here. Again, I'm taking benefit of the utility event, which is very useful for this type of a study. So what I'm doing, I'm bringing down the utility bus voltage to 40%, and then at 500 milliseconds, and then I increase it back at 1 second. So if I run this case, let me run this case. Actually, this is a low voltage right through demonstration. So what happens is that I have basically a battery, and I've put two different LVRT curves. So one of them actually requires to trip faster, the other one trips basically later. Now let's take a look at the results. I'm looking at a battery 1 and battery 2, and I'm looking at my megawatt, megavar, and current. What has happened is that at 0.5 second the voltage dropped, and once the voltage drops, my expectation is that typically the reactive power injected by the inverter goes up. So the current goes up, and the current the reactive component of the current goes much higher up because of the far right through capability. Keep in mind that those information about far right through is going to come from the FRT page of the inverter. And so what happens is that as the current goes up, the reactive power goes up, and typically the active power goes down. And so what will happen is that the inverter writes through, injects reactive power, tries to bring up the voltage. Now let's quickly take a look at the voltage here. Let's look at the battery PCC voltage. So what happens is that as you see that it tries to bring up the voltage a little bit, system is strong, so it doesn't come too much high, but it goes up. And then after that, what happens is that inverter passes the time period that is supposed to be riding through, so it's gonna trip. One of them trip faster because we set it to trip faster in the ride through capability, and the other one trips later on. So those settings are also here in the basically the controller of the inverter. That can be set for the far right through capability. So we have a timings that you define basically the characteristics for the FRT. Now, the other important things that when we are talking about doing transient stability with DRs, especially when it comes to the microgrid application, is the capability of a transient stability tool to be able to handle islanded system, as well as be able to do grid forming for the inverter. So ETAP has been always been able to do the islanded system for a long time because it's made originally for industrial applications, and we wanted to be able to do that. But on top of that, we are supporting the grid forming inverters. So what happens is that, so in this scenario, let's say, let me run a case. I have a case that we put a fault. This is a microgrid. We put a fault, we disconnect from the grid, basically the relay trips, we disconnect from the grid. So we are able, first of all, to operate in the islanded mode. So this is a case that we have a fault at 2 seconds, and then we disconnect from the grid. As you see, the rest of the system is energized. The inverter goes into the grid forming in these scenarios, and basically it tries to maintain the voltage and be able to maintain the frequency. So let me go here and again plot the batteries in this scenario. I'm again plotting the megawatt, megavar for the battery. As you see here, currently one of my battery, which is the largest one, battery 2, is set to switch to the grid forming. So it monitors the circuit breaker status. The moment it trips, it switches to grid forming. And as you see that the moment that basically after the trips, it switches to the grid forming, and actually the active and reactive power adjust themselves to maintain the voltage and frequency of the system. And as you see that battery 2 is in grid following, and it has a P and Q set point, so it always comes back eventually to its set points for P and Q. And but during the fault and during the disturbances, when the voltages are not stable, it tries to support by putting more reactive power to the system and active power during frequency variation to support the system. So again, this is a case. Let me also plot actually the frequency here. So if I plot the frequency of point of measurements for this and voltage, you're going to see the basically voltage and frequency as well. As you see that frequency drops to 99%, but it comes back and goes a stable 100%. Again, this is the grid forming application. And then the voltage during the fault dropped to 0 and then comes back to around the set point that we set it. We set it a little bit lower to make sure that we can lower the load and balance the system. So this was the grid forming basically demonstration. Again, this we use a generic model for our inverter here, but this model has better capabilities in terms of modeling the far right true capabilities and grid forming and following. And this is more useful for early stages of the projects where the vendor is not picked or the model is not available, and we want to use something for the design of the system. Another interesting feature that we added to ETAP 20 was support for Inrush current study. And basically in this study, we try to utilize transient stability module to estimate the magnitude and the decaying time constants of an inrush current. So inrush current typically happens when we are energizing a de-energized transformer. So basically we have a transformer that is completely open from both ends and we are trying to connect from one side. So what typically happens, because depending on which point and wave we are connecting the transformer and how much remnant flux we have in the transformer, the flux is the integral of the voltage. And if we basically connect it at a certain point that we integrate the voltage, and the flux may go above actually the knee point, and the transformer starts saturating and absorbing more magnetizing current. So again, if you just Google, you'll find tons of information about the inrush currents and how to model it and what are the different aspects of it. But as a quick example to show you here is that a transformer can absorb even up to 5-6 per unit of this nominal current during the energization. Even though the other side is open, and ideally you assume that there won't be any current, but it may absorb 6-7 per units depending again on the characteristics of the transformer and when we connect it. Now this is a case that it shows actually what happens, that we have a no remnant flux and we are closing at 0 point and wave, and as you see that as the voltage goes through starting from 0, we are integrating that, and flux can go up to 2 per unit RMS. So this results into the drawing lots of currents by the transformer, and this current is very much harmonical. Typically it has a great amount of second harmonic, and typally it's towards one direction, whether positive or negative. And as you see here, that the magnitude can go quite high. And it takes actually quite a bit to decay. It takes several seconds sometimes to decay. Now, when it comes to the system design, the systems needs to be able to actually tolerate that amount of current drawn, basically the harmonic content, as well as the protection system needs to restrain during this amount of current. This is way above the normal loading conditions. So typically this type of analysis is done in the electromagnetic transient analysis and EMT type softwares. And typically doing this study in EMT, it requires, first of all, those softwares are expensive. At the same time, it requires quite expertise to be able to do that. And what we provide as an alternative in ETAP, we are providing a mechanism to be able to, first of all, be able to estimate the peak value and also a decaying constant. So what we have done, we have provided a sophisticated algorithm within transient stability, which is a phasor-based analysis, but be able to somehow capture this non-linear basically characteristics of transformer within that to be able to calculate this peak value and decay indices. So in ETAP, you can actually go to the transformer, go to the protection page, and you can go to the magnetizing inrush part and add basically the voltage versus current or flux versus current characteristic in percentage. So if you define your characteristic here, and if you run the analysis, let's say if you energize this transformer, you can see that how the inrush current gets calculated, and you can plot that. So let's quickly take a step and do that. So let's try to run this analysis. So we are going to run a simple case where we are energizing a transformer. And typically, when we do the Inrush study, we select a lower simulation time step. Here, in this case, is 0.1 millisecond to get a better accuracy and capture the nonlinear characteristics of the transformer. So as we go here to the transformer T1, I can actually plot the currents. So this is actually, you see the inrush current. Typically, you can capture the peak value. Let's say in this case is around 9,500, 600, and you can always go to the crosshair and look at the value is around 9,000. And then you can also look at the time constant, that how long typically, let's say in this case, it takes about 2-3 seconds actually to go down, okay? So you see that the magnetizing current is around 20 ampere, while the inrush can reach close to even 10,000 ampere. So that's one case that you can actually study your inrush. There are many cases that in industry, they use a pre-magnetizing transformer to reduce the inrush current. And in ETAP, actually, you can do this analysis. So what happens is that, let me actually run the case for better illustration here, that what happens. So typically they use a very smaller size transformer. So in this case is typically 1/100th of the main transformer. So I have a 675 megavolt ampere transformer, and I'm using a 1/100th of that as a pre-magnetizing transformer. Okay, as you see here, what we do for pre-magnetizing transformer, we are closing the smaller transformer, let's say 0.5 seconds, and then we energize the second transformer through the first transformer. Then we bypass the first transformer, and then we open the transformer, the pre-magnetizing transformer. So what happens here is that there's an interesting phenomena happens here. So let me just plot the current of both transformer in this case. Let me uncheck everything and current from. So as you see here, first we energize the first transformer, the smaller transformer. So you're gonna see basically the inrush current, but because the first transformer is really small, it's gonna draw very little inrush current with respect to the utility size. With respect to its own transformer, it's still large, but with respect to the largest transformer and the utility, this current is small. Now that the first transformer is energized, we're gonna now energize the second transformer. Now what happens with the second transformer, because you have a very large impedance, because this transformer in terms of size is 100 times smaller, you are energizing this transformer with a very large impedance. So it's going to limit the amount of current that can go into this transformer. So the second transformer, when it gets energized, is going to have much lower inrush in this case. So as you see here, this case has 300 ampere versus the last time that we did this. Actually, if I go to the WI, this was WO without a pre-magnetizing transformer, and look at the T1, we had around 10,000 ampere. So we brought down 10,000 to around 300 ampere in this case. Again, that's a very good example of how you can actually utilize this module to verify that how your pre-magnetizing transformer can successfully reduce or effectively reduce your inrush current, or the size is correct and it works correctly or not. So it can be used at the design stage to size your actually pre-magnetizing transformer. By convention, EMTP type of analysis is used for inrush current study, which is expensive and complex, and ETAP offers an alternative approach within transient stability analysis. And this approach is acceptable for the purpose of, again, system design and protection setting, just to estimate the peak of the current and the decaying constant. So it's a very useful tool that if you don't want to go to the complexity of using EMTP type solutions. With that, let's summarize this webinar. We first reviewed the transient stability module of ETAP. In this webinar, we mostly focus on the distributed energy resources models and how they're supported in ETAP. We look at the legacy models, VEC models, the generic models that we had for the, let's say, over 10 years ago. And then we look at the newer models, VEC, basically latest second generation. We look at the IEC model for type 4A, type 4B, which are basically published around 2015, 14 and 15. We look at the power plant controller UDM. We look at the UDM for the PV, storage. Again, these WEC models and the European or IEC models are mostly for system planning studies. And then when it comes to the system planning study, we mentioned that ETAP has lots of great tools to be able to emulate different events at the, let's say, at the point of interconnection or at the utility connection. So that helps to bring the voltage down or up, or frequency down or up to a certain level for the testing purpose and for the simulation purpose, to make sure the system or your wind farm or your solar farm responds correctly or responds as expected, or see the impact of it to the system. The second aspect of doing a transient stability with DRs is the interconnection studies, where the focus is on the evaluation of a certain inverter technology or DR technology to make sure that it meets certain requirements, grid code requirements, standard requirements. And typically for this type of a study, vendor-specific model needs to be used, and we said that ETAP supports a concept of black box modeling. We provide generic interface, C++ interfaces that can be used by vendors to basically wrap their basically black box models to be able to use ETAP to exchange data for the voltage, currents, powers, and settings, and circuit breaker status as well. At the same time, sometimes the generic model is also useful where it's the earliest stage of the project, the vendor has not been picked, or the black box model may not be available. So we provide, we support those kind of basically generic models that you can do more detailed studies of FRT curves and low voltage right-through capability, tripping of the circuit breakers and timings, and how much active reactive power will be injected to the system. We also support grid following and forming, grid supporting as well within this generic model. Again, this is one step ahead to above the published models by the organizations to be able to support the clients and their needs to have a proper model for simulating their system. We also talked about the inrush current studies. The inrush current becomes more and more important due to especially even integration of renewables. We're expecting to have microgrids in the islanded fort to start with a black start, and we need to analyze to make sure that when we don't have a grid connection, actually their DRs, their transformers can actually get energized, connect to the system. So it's important to evaluate those currents. We showed actually demonstrated that how the pre-magnetizing transformer can be used or can be studied within ETAP to effectively reduce the inrush current. So with that, I'm done with my presentations, and I'm more than welcome to answer any question.